All right, so I guess we'll just pick it up where we left off last time. We still have the chapter 3, problem set number 2, that's not quite done. And then we're going to do the sample midterm, which is going to take a while. All right, so for this one, we had gotten up to 10, or 9 actually. So we're going to do the rest of these today. And then the sample midterm will be next. And just go get that open. All right, so this will probably take up the whole class, but all this reviewing. But if not, we can at least take a peek at chapter 4. But I suspect that all of this reviewing is going to take up most, if not all, of the class, which is fine, because once we're done with the sample midterm, then I can actually give you the real midterm. I'll post it up online, and then you can have a week to do it. It shouldn't take that long, but this way you'll have plenty of time. There's no rush. So first, let's finish up the chapter 3 problem set, and then we'll get into the sample midterm. All right, so let's see. So we left off with 9. Now here we're just doing the domain and the range. And so how do we do this again? All right, well, we have some formulas that are going to come in very handy. So remember here, this is a quadratic equation. And so we're set A equal to 2, B is -4, and C is 2. Okay. Remember, the form of a quadratic equation is always written as f of x equals ax squared plus bx plus c. So those coefficients are here, 2, -4, and 2. So in these types of cases, the domain is always going to be the range from -infinity up to +infinity. So that's pretty straightforward. We don't have to worry about that. It's the range that we have to pay attention to. All right, so let me find my symbol here for infinity. All right, well, there's a quick way of finding it. Two, 2, 2, 1, E, okay. There we go. All right. So from negative to positive infinity. What about the range, though? The range has a specific formula. So let's see. When A is positive, the range is, okay, so in other words, you don't have to really, there's no mystery about this one. It's a formula. And we've seen before that that formula has 2 parts to it, depending on whether or not A is positive or negative. All right, in the case of A is positive, the formula becomes, let's see, we've got square brackets. Whoops, nope. Square brackets. Man, I missed it again. Square brackets. There we go. All right, so f of negative e over 2a, comma, infinity. All right, infinity is right here. All right, that's it right there. So that's the formula for positive A. Now, of course, once again, these are the values of A, B, and C. So therefore, let's just leave it there. So we can extend this now to, oh, one more thing. I just realized this is not correct. I just realized the right bracket is supposed to be round, not square. Hold on. So I have to correct that. Hold on one second. So the left side is a square bracket, and the right-hand side is a round bracket because of the infinity. Okay, and so here we've got right here. No, wait a minute. Hmm. Oh, there we go. All right. All right, it's all set now. All right, so now we can just plug in the numbers. So first things first, negative b over 2a is negative 4 over 2 times 2, which means 4 over 4, which is just 1. Okay, now given the original function, f of 1 would, of course, be 2 times 1 squared minus 4 times 1 plus 2 equals 2 minus 4 plus 2 equals 0, as a matter of fact. Okay, so therefore, the range is just 0. Okay, from 0, and that includes the 0, by the way. All right, so we're finally done. Let's see what a nuisance that is compared to the domain. So anyway, once again, let's recap all of that. We identified A, B, and C. We know that the domain is everything from negative to positive infinity, and that's because there's no value of x that would cause this function to be either imaginary or undefined. Because A is positive, the range is this interval from f of negative b over 2a, including that value. And then on the right-hand side, we have infinity. So we solve for negative b over 2a and come up with 1. And then that gets plugged into the function. We solve for f of 1, and the value is 0. So therefore, the bottom line, or conclusion, is that the range is everything from 0 up to infinity, including the 0. All right. Okay, good. So let's see what's next. Okay. So how about this one? We've got A equals 3, B equals negative 6, C equals negative 9. So as always, with a polynomial, the domain is the interval from negative to positive infinity. Okay, so that's easy. And just like before, since A is positive, this is our range. Okay, so but this time, of course, negative b over 2a is different. We have negative 6, comma, negative 6 over 2 times 3, which just by ridiculous coincidence is also equal to 1. 6 over 6 equals 1. All right, so we're looking for f of 1 based on this function. So f of 1 would be 3 times 1 squared. Hold on one second. It doesn't matter, just as long as it's positive. That's all that it means. You're just saying that if A is positive, use this formula. Otherwise, use the other formula that we had last time, which was where we reversed the two, and we had negative infinity up to positive. Let's see. All right, hold on. Let me go. I'll show it to you in the slides. All right, where did we have that? All right, I'll tell you. Let's search for it with the search as long as we have it. All right, let's see where we find it. It's here. I know it's here somewhere. Hold on. Okay, here we are. So this is in 3A, page slide 75. The domain of a quadratic function equals all real numbers. The range depends on the size of A. So if A is positive, then we use this formula for a range. If A is negative, then we reverse it. That's all. In other words, here we have this function as the lower limit. Infinity is the upper limit. Whereas here, the lower limit is negative infinity, and this number becomes the upper limit. Okay, so basically the way you have to think about it is that if A is positive, this means that the parabola is facing up. So let's say this is, whatever this value is, this is my f of negative b over 2a. And what this is saying is that y cannot fall below this value. So let's just make up a number here. Suppose this is 3. What this is saying is that y is greater than or equal to 3, or we could write it in the interval form as y falls somewhere between 3 rather, and positive infinity. Whereas in the other case, where a is negative, the parabola is facing downward. So wherever it reaches its maximum value, this is also f of negative b over 2a. And let's just say that that's equal to 4. This time, though, you can see that y has to be less than or equal to 4. It can't go above 4. It's everything down to negative infinity. So we can write this in interval form as negative infinity, comma 4. And so that's the logic behind this. So it's just a question of whether the parabola is facing upward or downward, whether this number here is the upper limit or the lower limit of y. And if it's the upper limit, the lower limit must be negative infinity. If this number is the lower limit, as it is here, the upper limit must be positive infinity. So that's really what this is all about. What you're essentially just doing is saying, is the parabola facing up or down? And that will determine what the range is. So here it's written as a positive. In other words, instead of saying the words positive, I wrote a greater than 0. Yes, so in other words, you have to think in terms of the formal definition of any quadratic equation is this right here. So the a, b, and c are coming from the coefficients of this equation. In other words, whatever the coefficient of x squared is your a, the coefficient of x is your b, and the constant is your c. So that's where those numbers are coming from the original quadratic equation. All right, so they're all done the same way. So when you see the b, a, and a here, they're coming from the original quadratic equation. The a, remember, is the x squared coefficient, and the b is the x coefficient. Okay. So, and this statement here, a greater than 0, it just means that a is positive. Over here, I mean, and so it's just another way of saying positive. All right, so this one was, oh, we're still in the middle of this one. Okay, 3 times 1 squared minus 6 times 1 minus 9 equals 3 minus 6 minus 9, which is minus 12. Okay, so what that means is that the range is everything from negative 12 up to positive infinity. Let's get that infinity in there. Now, I almost forgot about it for a second, but we can confirm this with Symbolab. We can take a look at this. It'll show us exactly what this looks like so we can visualize it better, which I think is a great idea. You know, it takes a while to get used to learning how these functions look. So when we have something like this, 3x squared minus 6x minus 9. Let's see what that looks like. Okay, so you can see the logic here. This point is 1 comma negative 12. So there's no point on this function where y can be less than negative 12. In other words, you see how y has got to be negative 12 or above, but it can't fall below that point. And so that's why we say that the range is negative 12 up to infinity. The domain, on the other hand, is the entire real number line. There's no value of x that does not work here, but the range is the tricky part. So we can see it does start here where y is negative 12, and then we go up after that. And so y will continue to increase all the way up to positive infinity. Yeah, so yeah, I definitely like having these graphs available to us. It's so much easier to visualize it than just looking at the equations. All right, and then it looks like we have one more. Okay, so what about this one? So first things first, a equals 2, b equals 6, c equals negative 3. And we know everything in chapters 1 through 3. That's a good question. Everything that we've done up to chapter 3. And then 4 will be for the next midterm. 4 plus. We'll have to figure that one out. I think 4 and 5 is the second midterm, but the first midterm is definitely 1 through 3. All right, so anyway, so let's get back to this. So we know the domain automatically is negative to positive infinity, but the range, and once again, just by coincidence, a is positive, a right here, a is positive, and so therefore we use this formula. So let's plug it in. B, negative b over 2a is negative 6 over 2 times 2, which is, of course, negative 6/4, or we may as well reduce it to negative 3/2. And now we need to solve for f of negative 3/2. So we've got 2 times negative 3/2 squared. Oops. Plus 6, negative 3/2 minus 3. So 2 times 9 over 4. This time, for this one, we've got minus 18/2 minus 3. So let's turn that into 18/4 minus 18/2 minus 3. So for something, oops, we may as well have a common denominator. Let's choose 4. That means this one is 36/4 minus 12/4. And so what is that going to give us? 18 minus 36 minus 12 is, wait a minute, 18 minus 36 minus 12 is minus 30/4. or we might as well reduce it to negative 15 halves. Okay, so that's f of negative b over a. So that means that our range based on that formula is negative 15 halves up to positive infinity. Okay. Excellent. All right. So now what we're doing next, oh yeah, division. Okay, well, this is, not that bad. These are not that difficult. And for the most part, they will all have remainders, not every single time. But what we're going to do is just basically divide one expression into the other. Oh, I almost forgot. We're supposed to double check this with Symbolab. Let's take a look at this thing. 2x squared plus 6x minus 3. Minus 3. All right, beautiful. So right there, it'll tell it right there, negative 15 halves is the value of y. That's the minimum point on this function. So therefore, y can never fall below negative 15 halves. So that's why our range is everything from negative 15 halves up to infinity. All right. Now this is a technique that we'll be following. Okay, so what you have to do is line it up. So you'll have x squared plus 5x minus 1. So what I'd like to do, I need to eliminate these terms one at a time. So I'll start with x. Why x? Because x times x minus 1 is x squared minus x. Now I want to subtract this result, but I have to be careful because that means this term becomes negative and these drop out. This becomes positive, and I end up with 6x minus 1. Now I'd like to get rid of that 6x. How do I do it? Let's try plus 6 here. And 6 times x minus 1 is 6x minus 6. I have to subtract that. This becomes negative and these drop out. This becomes positive, and I have a 5. So this is the final result. The quotient is this piece. The remainder is this, the 5. Okay, so basically what this is saying is that this expression that we started out with is the same thing as x squared plus 5x minus 1 divided by x minus 1 can be rewritten as x plus 6 plus 5 over x minus 1. They mean the same thing. Now, I don't know if this is any more useful than what we have on the left. The only time this is really helpful, I think, is when there's no remainder. And that way we have a much simpler expression. But still, sometimes it can be very helpful to be able to divide one polynomial by another. But here, the expression that we ended up with is not a whole lot simpler. In fact, it's even kind of messy. But for our purposes, we just want to understand how to identify the quotient and the remainder. Now, this is making me curious. I'm wondering if Symbolab can do this. let's say I said to Symbolab, hey, Symbolab, I want you to do this for me. X squared okay, let's see what it can do. X squared plus 5x minus 1. Hold on, it's acting up on me. So it's plus 5x minus 1 over x minus 1. Now, what I'm going to do is just say hit go, and I want to see how it reacts to that. Yeah, see, it's giving us everything except maybe what we actually want. And oh, it's a weird looking graph, but I'm not sure. Let me just try simplify. No, it doesn't seem to understand what I just did. Let's try solve for. No. All right, let me try this one more time. If this doesn't work, then I'll just go on to something else. I was just wondering if this could actually be a helpful tool for these types of situations. There's probably a way. I just don't have that much experience with this thing. It has its own little quirks that you have to get used to, like all software packages. Now, I'm wondering how it will interpret simplify in this case. No, it doesn't. It's not really getting the point. That's all right. I'll tell you what, let's try this one. Let's try solve for it. It might understand now. No, I guess there's only so much it can do. That's all right. That's all right. We know how to do it. I thought it might be better at this, but I guess not. It's kind of a shame, but I mean, I know there are packages that can do this. All right, let's try this one. All right, let's try this one for x. All right, so again, the goal is to eliminate these terms one at a time. Let's start at the beginning. What can I multiply this expression here on the left by that will give me a 4x squared? How about x? So 4x squared plus 2, if I multiply the x by this expression, I have 4x squared plus 2x. When I subtract, this becomes negative. This becomes negative. And remember, after every one of these subtractions, you always bring down the next terms. In other words, this subtraction leaves me with negative 12x, but don't forget, this needs to be here too. So I forgot to mention that up here. Every step along the way, like here, for example, when I subtracted, I got 6x, then you bring down the negative 1 as well. Okay, so that's how this works. So the same thing is going on here. Now I've got negative 12x plus 6. So I'll put minus 3. Why? Because that gives me minus 12x minus 6. When I subtract, this becomes positive. This is positive, and I'm left with 12. So the quotient is x minus 3 and the remainder is the 12. And that's all you need, okay? All right, there's your quotient on top. There's your remainder on the bottom. All right, I think we have a couple more. How about 15? There we go. So we've got x minus 5 divided into 2x squared minus 9x minus 5. Okay, so we need to eliminate the 2x squared. So why don't we try 2x? 2x times x minus 5 is 2x squared minus 10x. Subtract. That means this is negative. This is positive. Bring down the negative. Oh, look at this one. Oh, what do you know? We got lucky with this one. So the quotient is x minus 2x plus 1, and the remainder is 0. So what that means then is that this expression just equals 2x plus 1. The reason for that is because this original expression in the numerator equals, well, now we know, equals x minus 5 times 2x plus 1. So therefore, if I take that ratio and divide by the x minus 5, of course, it's going to leave me with 2x plus 1. Okay, well, that was rather satisfying, I must say. So this time we really did reduce it to a much easier form. And so it was worth our while to do the division. All right, one more. Now this one, we'll see. You never know. It's hard to tell when you just look at these things if there's going to be a remainder or not. I mean, it looks promising because that 14 and that 7, but we shall see. So to get rid of this 3x squared, let's try 3x. So that 3x times this expression, 3x times x plus 7 is 3x squared plus 21x. So I subtract. This becomes negative. And here this is negative. I've got 2x. I bring this down. Plus 14. Oh, it looks good. Because now if I multiply by 2, what do I have? 2x plus 14. They both drop out. Look at that. So I've got a quotient. It's 2. Remainder is 0. And that's it. Okay, so those are done. Now, what's left? Oh, inverses. Yes. Okay. So inverses are interesting. And these, by the way, we can double check with Symbolab. Remember how this works. Basically, for all practical purposes, what you're doing is this. You start out by rewriting this as y equals whatever you've got. And then basically you reverse the x and the y. Okay, so let's do that first. Replace this with x equals radical 2y plus 1. Now solve for x, or y rather. So how do I do that? Well, first let's square both sides. Okay, then I can subtract 2 from both sides. Because, oh, actually, no, I'll just subtract 1. Let's leave it like this. This is easier. And then I can divide both sides by 2. So what this means then is that the initial function, f of x, was 2x plus 1, radical 2x plus 1, f inverse, which is written f minus 1 of x, therefore equals x squared minus 1 over 2. Now, it doesn't ask us to prove this. If it did, to prove this, and I'll just mention this one more time, to prove this, we must show that 2 things are true. One, f of f inverse of x equals x. And number 2, f inverse of f of x equals x. So I'll tell you what, let's do one of these just to get some practice. After that, we'll just calculate them. So for example, here, f of f inverse of x would be, you start with the original function and all the x's are replaced with the inverse. Okay, so in other words, the original function was square root of 2x plus 1. Wherever you see an x, replace it with f inverse of x, and then the rest is just algebra. So the inverse that we found was x squared minus 1 over 2. All right, now we keep our fingers crossed and hope that this ultimately proves to be equal to x. Let's see. Well, the 2's cancel out. Oh, I think it's looking good. Yeah, this is it. So we just proved one of the 2 conditions. Okay. But that's not enough, is it? No, we still have to prove the opposite condition, that f inverse of f of x is also equal to x. All right, so let's do that. And remember, if it doesn't say you must do this, then you don't have to do it, unless you just want to use it as a double check, and that's fine. In fact, I applaud that, but it's not absolutely necessary unless it says so. So then let's try the opposite condition, f minus 1 of f of x equals x. So f inverse was right here. Let's see, it's x squared minus 1 over 2. F of x is the square root of 2x plus 1. 2x plus 1. All right, so now what we're actually doing is, for here, replacing all the x's with f of x. Okay. So the radical 2x plus 1 is squared minus 1. And then what does that turn into? Well, clearly that's equal to 2x plus 1 minus 1 over 2. 2x over 2 equals x. All right, and so we just proved that this is correct. All right, so this must be the right answer right here. I think Symbolab can do this, though. Why don't we just double check? Oh boy, you see it says here inverse. Let's see. I'm dying to know if it can actually do this. I think I have to include the f of x equals radical 2x plus 1. There it is, x squared minus 1 over 2. Wow, I'm impressed. Woohoo, it can do it. Interesting. Now it doesn't, oh, it does. Yeah, it goes through the steps. That's kind of interesting. Now, you know, if you notice, I just realized eventually that if you look over here on this lock, I think what they're basically telling you here is that they're giving you a lot of the information, but not all of it. If you really need more details, you can actually pay them. Well, it doesn't, okay, well, it's not so bad. $1.99 a week. It doesn't look that bad. $29 a year till it's canceled. You can actually subscribe to this thing and get a lot more information out of it. If you're going to be taking a lot of math classes, it might be a good investment. But yeah, I'm pretty impressed with it, considering, you know, it's free on the internet. It's not exactly Mathematica, but yeah, it's kind of nice. All right, well, let's get the rest of them done. All right, so once again, so what are we doing here? First, rewrite it. Y equals radical 3 minus 4x. Okay, now, of course, what you're doing is you are reversing the roles of the y and the x. So, in other words, wait a minute, hold on. Oh, okay, reverse x. I wanted to see how I forgot how I explained it before. Replace, or actually not replace, reverse. That, I think that's the best way to explain this. Let me change this one up here. Not reverse, well, yeah, reverse, that's right. Reverse the x and the y. That's better. Right, and then once we've done that, solve for y. That's better. All right, now, of course, it might be a pain to do this, but it's just, I mean, the process is very straightforward. So let's square both sides. Subtract 3 from both sides. And now we divide out by that -4. Okay, so the original function was radical 3 minus 4x. Therefore, the inverse is the one we just solved for. And that worked out to be x squared minus, oh, you know what? There's a negative. Let's write it like this. I think that's better. See, there's a -4 in the denominator. Let's put it up here. I think it's just easier that way to see what's going on. All right, and since we have access to it, we might as well double check this with Symbolab. We have 3 minus 4x under the square root sign. And it comes back with -x squared minus 3 over 4, exactly what we have. But you notice they're going through the same way that we are. It's very simply replace x with y, solve for y. Oh, okay. So if you missed anything, you can watch the video or look at the solutions when I post them. All right. Anyway, so yes. Okay, so that's good. So it's not only telling you the answer, it's showing you how it was done. That to me is the most important thing, which again is still surprising for a free product like that, or at least the part we're looking at is free. Look at all this other stuff it has. Man, it even has science. In case you find yourself in a physics or chemistry class, well, there you go. Wow, it really does have everything. Groups, I wonder what that is. Practice. Graphs, we know about the graphs. All right, so let's get to the next one. So once again, replace. Reverse, I did it again, reverse. X and Y. And so once we've done that, and now solve for Y. Okay, so let's see. Let's subtract the 9 from both sides. Square them both. Add 4 to both sides. And then, of course, divide by 4. Okay, so the original function was 9 plus radical 4x minus 4, and the inverse that we've just discovered is x minus 9 squared plus 4 over 4. All right. So I'll give you a minute to catch up, and then we'll double check on Symbolab. How about that? Okay, let's check it out. 9 plus radical 4x minus 4. Okay, let's see. Oh, you know what they did? Okay, I know. See what they did was they wrote it out, the x minus 9 squared. They expanded that. X minus 9, that would give us x squared plus 18x minus 81. If you use FOIL on this, you would get first is x times x, O is minus 9x, I is also minus 9x, and last is 81. And that comes over here. And then, of course, we also had that 4. So what did they get here? Oh, they've got something different. Oh, no, I just wrote it wrong. Sorry, no wonder I copied it wrong. I was going to say something's wrong. There's something, sure is. 18 squared minus 18x plus, that's better. So we have 18x squared minus 18x plus 85 over 4. Okay, so in other words, what we had up here is correct, but they wrote it out in a slightly different form. It doesn't matter. They're both fine. All right, very good. So if you have an answer like this on your test, this is fine, but they chose to go ahead and expand this square term, and this is the final result. All right, one more, and then this section is done, and then we can dive into the sample midterm, which of course has a little bit of everything. It'll be like a blast from the past. It'll be like going back to February, remembering what we were doing all the way back then. All right. So of course, first things first, write this out as y equals 5 plus radical 6x minus 8. Reverse x and y. This becomes x equals 5 plus radical 6y minus 8. And now solve for y. All right, so of course we'll start by subtracting the 5. Then we can square both sides. We can add the 8, add the 8 to both sides. Then we can divide out the 6. And that's it. So if the original function, since the original function was 5 plus radical 6x minus 8, the inverse, as we discovered, is x minus 5 squared plus 8 over 6. All right. So let's give it a shot on Symbolab. Now, of course, it looks like they're going to expand it, and we'll confirm that in a minute. All right, so we had 5 plus radical 6x minus 8. And let's see what it has to say for itself. Okay, so all right, so let's do this. Let's confirm that they're the same. X minus 5 squared, if you use FOIL. X squared for F. Outer is minus 5x. Inner is minus 5x. Last is 25. So therefore, the solution that we found x minus 5 squared plus 8, 6. So we'll replace that x minus 5 squared with x squared minus 10x plus 8, all divided by 6. And we have x squared minus 10x plus 33 over 6. So, and that's what they have. X squared minus 10x plus 33 over 6. That is the equivalent version of our inverse. All right, so that ordeal is over. So now, at long last, we can finally bring out the sample midterm, what we've been waiting for all this time. Okay, now you've been dying to see it. So I'll give you a minute to catch up, and then we'll jump ahead and start looking at our sample midterm. All right, so I'll assume you're all caught up. I'll be posting these on Blackboard, Moodle, of course. And so let's go ahead and let's see. I have to just do one thing here. Okay, so let's begin. Now, the short answers, of course, could be anything. And now keep in mind, this is all taken from all 3 chapters. So, what I think maybe it would be a good move to do is to open up or get these notes available, just so I can remind you where this information is found if you've forgotten when we covered this stuff. Okay, so you never know. I mean, you might say, well, I remember doing this, but I wish I could find it. So it's important to remember where all this information is found so that when you're doing the test, you won't have to spend all your time searching for it. Okay, so I think we have everything open. Nope, we still need 3A. Hold on. All right, so yeah, we should be able to find anything that we need if we need to. All right, so let's get back to this. So first of all, what's the slope of a vertical line? Now, this is kind of a trick question because it's undefined. Why is that? Because if you look at a vertical line, for example, x equals 3, the slope, as you know, is delta y over delta x. And what you'll notice here is that delta x is 0 throughout the entire function. Well, it's not even a function. That's the other thing. It's not a function. Delta x is always 0. Therefore, the slope is undefined because it requires division by 0. All right, so obviously we can't have that. Now, what's the equation of a line written in point slope form? All right, so if you've forgotten, there are 2 ways of writing the equation of a straight line. We know in fact, so let's go back to chapter 1 and quickly review this. Let's use our friend, the search engine. Okay, well, that was not chapter 1, clearly. This is what I mean, though. I mean, it helps if you remember where everything is. I should probably write an index for these notes. I think there might be a way. I think there might be a way of doing that. I should investigate that. Okay. I'm not sure if it's, yeah. Well, let's see. See, the problem with the search engine, though, is that it's not going to pick up on equations. But that should still have appeared somewhere. I would have guessed it would have been in 2. Well, we'll probably just have to use the old-fashioned approach. Oh, you know what? I'm wondering if it's possible for it to pick things up in the titles. Let me just try this. And there's also a dash in there. Okay, that was the holdup. There was a dash in there. Okay. Anyway, here's the point slope equation of the form. Okay, so in other words, in addition to the one we're used to, which is, of course, sometimes called the slope intercept form, point slope form means you're using the slope and one point. It means the same thing, of course, but sometimes it's more convenient. Okay, so that was good. Now, the complex conjugate, the way it works is that for any complex number, let's say a plus bi, the complex conjugate is a minus bi, and vice versa. In other words, they are complex conjugates of each other. So in this case, the complex conjugate is just 3 plus 4i. Right? Now, where did we find this information? Now, this one, I'm quite confident it appears in 3a when we were talking about complex numbers. So let me just use the search engine and see if it actually works this time. There it is, right there. So this is slide 8. In fact, you know what? Let me do this. Just in case you need to double check this. I'll sneak that in there for you. How about that? Now, I to the 7th power. Well, that's interesting. What you might want to think about doing in a case like this is writing them all out. There's a chart here. I to the 1 is obviously I. I squared, though, is -1. Why? Because I equals the square root of -1. I squared equals the square -1 squared, and then we have -1. I cubed would just be then -1 times I, or -I. Okay, so in other words, I cubed equals I squared times I. Okay, and then that being the case, I to the 4th is 1 because I to the 4th equals I squared squared equals -1 squared, which is 1. And from this point on, it just forms a repeating cycle. In other words, I to the 5th is I. I to the 6th is -1 because I to the 6th equals I squared. In other words, every 4 exponent, when the exponent goes up by 4, the value returns to its original value. So I7 is -I because I to the 7th equals I cubed. And if I'll just finish this in, even though we're not asked to do that, that implies that I to the 8th is 1 because I to the 8th equals I to the 4th. So we had a chart showing this somewhere along the way. Let's go find it. No, it's here. I know. Oh, I think I found it by accident. Here it is. So start with slide 6. This is 3A, slide 6. just in case you need to go double check it. Okay, but the answer we're looking for is -1. But I just wanted you to remember how all this actually works. And remember, it goes through a cycle. Every 4 i's, it starts all over again. All right. One of the interesting things about complex numbers. Now, how's the axis? Oh, we just did this a while back. The axis of symmetry equals, you probably still have this one memorized. There you go. X equals -b over 2a. So where did we discover this? This would have been towards the end of 3b. Let's see, where exactly was that? Oh, no, it was 3a. Okay, man, this 3a was a big chapter, wasn't it? Hold on. There we go. So this is 3a, slide 54. Just in case you want to go back and reread it. Okay. So when you're studying, when you're putting together your studying notes, you may want to organize this in your own unique way, whatever works for you, but you have to be able to find this. And I don't want you to have to spend all day looking for it. So therefore, we might as well write these down as we go along. Now, the domain, now, of course, we just got through doing a bunch of these. The domain is automatically equal to -infinity up to positive infinity. But where did we find this out? All right, let's remind ourselves where this information is being stored here. Let's see. No, that's the domain of a rational function. We need a quadratic. Okay, where did it go? No, let's try that again. Let's go for quadratic. I think we're getting warm. Here it is. 3a, slide 75. That's right, 75, just making sure. All right. So again, if you want to read up on that, it's 3a, slide 75. All right, so let me change this slightly. All right, so this way I'm kind of helping you do some research here, just to make sure you know where everything is located. All right, the range of the absolute value function. Now remember what that thing looks like. If you look at this graph carefully, you'll see that you can have an absolute value of 0, but no negatives. Okay, so in other words, the range would have to be everything from 0 up to positive infinity. Including the 0. Okay, in other words, the y's Y can be any positive number or 0. All right, and that's what we're looking for with the range. Now, if you want to review this one, I think that may have shown up in, let's find out. This is 3A. No, this must have shown up earlier, like maybe chapter 2. No. All right, if you insist, let's try this one. Ah, there we go. 64, although it doesn't explicitly discuss the range at this point. So I guess, well, this one we'll have to figure it out. But anyway, so now one-to-one function, we definitely went over this early on, maybe chapter 1. So if you look in 1, here we go. Oh, I just saw it. What is a one-to-one function? A one-to-one function means each element of the domain is assigned a unique value in the range. Okay, so what would be the quickest way of writing this? By the way, this is chapter 1, slide 43. Okay, that sounds good. I would take those as, yeah, those are all fine. So, but we can formally say that this is a function where each element of the domain is associated with a unique value of the range. So the example I gave in the slides, which I really like a lot, for example, a function that assigns a social security number to each person will be one-to-one. Because you can't have more than one person with the same social security number. It's different with birthdays, of course. More than one person can have the same birthday. So people to birthdays is a function, but it's not one-to-one because you can have multiple people with the same birthday, obviously, but not social security numbers. So that would be an example of a one-to-one function. And by the way, if you want to make up an example, that's fine too. When you're trying to explain yourself with these, when there's English involved, there can be some ambiguities. So if you want to make up an example, that's fine. But I would stick with the Social Security unless you can think of another one in the real world. It might exist, but that it's kind of unusual. Oh, wait a minute, I have one. How about, see, this one almost works. How about fingerprints? Why doesn't that one work perfectly? Does anyone know? Or DNA for the same reason. Why doesn't DNA, why is it not perfect? Because of twins, that's right. Twins have the same fingerprints and they have the same DNA. Yes, they do. Okay, so therefore that almost could have been a one-to-one function if we leave out identical twins. Other than that, that would have been an example. Okay, so that kind of throws a monkey wrench in our example. All right, let's go back and revisit the reciprocal function. This should probably be in chapter 1. Yeah, there it is. So here's our reciprocal function. Yeah, Bond villains with advanced technology. That's right. Ooh, they can do a lot of evil things. That's right. So, yeah, in the future, supposedly they're going to get rid of fingerprints and replace them with retinal scans. I don't know how or why, but that's what they say. But it'll be the same problem though. Twins would tend to have, I'm sure they would have to have the same retinal scan. But I don't know. I guess it's easier just to read it. If you ever had your fingerprints taken, you know it's kind of a nuisance. You have to roll your finger around to make sure they get all the little circles in there. In fact, that reminds me, the iPhone, I think they may have given up on this. At one point in time, it was actually possible to log into your iPhone with your fingerprint. And I remember it did not work very well at all. And now that I think about it, I've got a relatively new one here, and I don't ever remember seeing that in there. Does anyone happen to know anything about that? Did they finally give up on it? Oh, this requires some, hold on one second. I think we can spare 30 seconds for something silly like this. Um, iPhone stop using fingerprints to log in. Yeah. Oh, that's right. It ditched the Touch ID in favor of Face ID. That's what happened. Well, because honestly, I mean, I never found the fingerprint worked well at all. Yeah, in fact, I have a new iPad over here, and shockingly enough, it actually works pretty well with the facial recognition. I can tell because it recognizes me whether I'm wearing my glasses or not, and that surprised me to no end. Um, Most likely, all the more high-end MacBook laptops and all the rest will use the facial recognition. So it offers you the option of using your face, or else you have to. If not, you can still punch in the code. But it actually is very very useful. It works well. I mean, I've had problems with it before. This one actually is pretty good. I don't know what they did, but they really improved it to no end here. So you can feel free to use it. Yeah, the fingerprint was almost a farce. It was so awful. So this is probably why they're talking about retinal scans or facial scans. I don't know. They're looking for certain things, and I don't know what they are. But apparently, there's just some parts of your face that are unique to you, and they know what they are. So I don't know anything about it, but anyway, let's get back to work here. Um, so here's the reciprocal function. Let's take a look at the picture. Now, based on this, you can tell, I guess. Let's get that out of here. We wanted to know. Oh, the domain. Oh, okay, okay. The range is actually all the real numbers, but you can see the domain is different. It is cool. It's like I remember the first day I opened it up and took it out of the box. It made me take a picture of myself before it let me continue setting it up. And it took a while. It was really wild. It was like science fiction going on there. All kinds of scanning was going on, and but it works really, really well. In fact, it really just needs a glance at you. It doesn't need to sit there and say, well, maybe that's you, maybe it isn't. It's just like boom, automatic almost that it says, oh, that's you. Don't worry about it. It would be interesting to see if we could find out what exactly it's looking for that makes you so unique compared to everybody else. But anyway, but yes, just by looking at this thing visually, you can see that X cannot be 0. All right. So in other words, and you can see why, because X equals 0 would lead to division by 0. So in this case, the domain, you can write it in interval form as -infinity. Oops. Comma, -infinity, up to but not including 0. And then we need the union symbol, which is, it's here somewhere. Hold on, I have to go look it up. Two A. see, I forgot. This is one way in which somehow Microsoft has screwed this thing up royally. Um, they somehow they've got this thing here that's supposed to represent a union. That is not the union. And I don't know. All right, let's try this. Oh, okay, no. It says here, look at this. You have to use, for the Windows character map, it is a semi-clunky process. Oh, for God's sake. I would say semi-clunky doesn't begin to describe it. You would think that this would be one of the most important symbols. This is really annoying, I can tell you. Oh, do you have an idea? Yeah, that's true. I don't know. I just think it shouldn't be such a pain in the butt to do this. Nah, all right. I'll do it. I'll compromise my integrity here. And all right. I don't like it, but we don't want to waste all morning on this. Just because Microsoft is totally incompetent. All right. So you're just leaving out the U. And I'll just make a note here that the reciprocal function, God, those imbeciles, is found on slide 71, chapter 1. Okay, now, here we go. What type of function has the property that for every x, f of x equals f of negative x? Okay, so for that one, we're going to go back. Probably this is chapter 1 territory. No. All right, maybe it's chapter 2. It's either an even or an odd function. I'll give you a hint right there. Yeah, okay. Maybe it's 3b. Maybe it's 3a. All right, it wants to be a pain. All right, now remember last time the issue was that there was a dash involved. Let's see what the excuse is this time. Jesus. You know what I'll do? I'll just look for the word odd. Maybe it's capable of doing that. Wait, hold on. All right, I'm just going to tell it to look for the word odd. Let's see if it can come up with it. It's either odd or even. Okay. Let's try 1b. This is why I'm doing this, by the way, because you don't want to. There it is. Now, why did it not identify this for me? I don't know. I don't know what the problem was. The search engine apparently isn't very bright. It was right there, but it was in the title. I think that confuses it. Anyway, so we're looking at this is 1b, slide 25. Oh, and I just realized this one, I think I messed this up. This one that we were looking at earlier was actually 1A. Okay, that's better. All right. So anyway, so here's what we're going to see. Let's just go back since we found it. Let me just copy this right into the document, just as a reminder. So just, that was meant to be a quick review. And so therefore, it should be clear that in our case, if f of x equals f of minus x, therefore, the function is even. All right, so in other words, that's what we're looking for. It's an even function. All right, so now, if the two lines are perpendicular, the relationship between their slopes for two perpendicular lines, the product of their slopes is -1. That's how we know they're perpendicular. So dare I use the search engine for the word perpendicular? All right, I don't know. I'm starting to have doubts about this thing. It's probably in the linear. Let's go to 2. Oh, it accidentally showed it to me. All right, this is chapter 2, slide 55. Okay, for your reference. Now, the range of a quadratic function. Okay. Now remember, we just did a bunch of these, didn't we? Yes. So where did we find this in the slides? That was this was probably in 3A. Oops, I think I went too far. It's in this neighborhood. Let's just jump ahead here a little bit and find it ourselves. No, here it is. Here it is. Okay, so they wanted to know the range. Okay, so remember how this works. We've got in 3A, here it is. All right, so let's copy this in here once and for all. That way you don't have to keep scrolling around for an hour looking for it. Oh, and while we're at it, this is chapter 3A, slide 76. Okay, and then for a negative A, okay, just in case it shows up. All right, that should do it. So now for, in this case, A equals 3, B equals -2, C is 1. And so we know that A is positive. Therefore, the range is this one. So we have to figure out f of A, negative B over 2A is minus a -2 over 2 times 3, which is 2 over 6, which is a third. F of 1/3 equals, all right, here we go. All right, so let's plug those numbers in and see what we get. 3 times a third squared minus 2 times a third plus 1. 3 times a ninth minus 2/3 plus 1. That's 3/9 minus 2/3 plus 1 equals 1/3 minus 2/3 plus 1 equals 2/3. Because let's see, yeah, minus a third plus 1, 2/3. All right, great. So therefore, the range is so let's type it into the formula. One third up to infinity. Okay. Wow. Okay, so that was kind of right. Now we're ready for the problems. Oh my God, can you imagine how scary these must be? All right, so we'll carry on. All right, well, of course, I think we should have our break in a minute, but we'll carry on with my new tradition of identifying where all this information is found in your slides so that when you just go to study, you can easily find everything you're looking for. And along the way, you should probably make up your own notes anyway, just to help you find everything you're looking for. And of course, go through and practice with the practice problems, practice with this, make sure you're getting all the same answers. If you want to fool around with Symbolab, that's fine too. Wow, these, there's a lot of them, aren't there? I did say earlier, I wasn't positive we would be able to finish this today. If not, I'll tell you what we'll do. If we don't finish this today, I'll post what we've done and I will post the midterm, but then you can have another week to do it. All right. I want to make sure that you have a week after we're 100% done with this. So if we don't quite finish it today, not a problem. I'll post the solutions that we have already and I'll post the test as well, but then you'll have an extra week to do it. Does that sound fair? Because I'm not sure if we're going to finish this. There's a lot here. But all right, so why don't we knock it off for a break, and then when we get back, we will carry on and start the problems, and we'll take it from there. Okay?
to oh, she lied.
What?
She lied.
No,
Stop.
I'm
Don't
joking.
always be so negative. No.
Red. What? Whatever.
Yo, man, you think that's a person? Well, just because you do it well.
Okay, here we go. So what we have to do is figure out if each of these is a function. All right, now let's go back. This would have been one of the first things we did in chapter 1. All right, so now there's right at the beginning when we define what is and is not a function. So first of all, any set of ordered pairs is defined as a relation. The question is whether or not the relation is also a function. Okay, so what does it take to be a function? Well, we have a domain and a range, of course. What we want to know is if each element in the domain is assigned a unique value in the range. So we can have the domain can have only unique values, but the range can have the same values more than once. Okay, so like for example here, this is a function because each element in the domain is associated with exactly one element in the range. But on the other hand, this one is not a function because x in the domain has been assigned, x equals 1 rather, has been assigned both 5 and 10. Okay, so that means this is not a function. And then we have another one where this is also not a function because x equals 1 has not been assigned any value of y. So what we're aiming for is each element in the domain must be associated with exactly one element in the range. And if more than one is not good enough, less than one is not good enough, it has to be exactly 1. So therefore, when we look at these examples, the first one clearly is a function. Okay, this is a function because each x is assigned a unique value of y. Specifically, y equals 2x plus 8. So that might be the best way to explain that, because each element of x has been assigned precisely one value of y. Now here, it's a little more challenging because we have to look around and see what elements are in the domain and what elements are in the range. So if you look at it very carefully, you'll see that each element in the domain, these are the elements, let's put these in order, -0, 1, 2, and 3. And each one has been assigned. In fact, you know what, it might even be easier to do it this way. Why don't we draw a picture like we did in the slides, just to see what it looks like. Here's x, the domain. Here's y, the range. So we have, just to be, let's try to put these in order. How about that? -1, 0, 2 and 3. Over here on this side, -1. Let's see, what do we have? We have 1, 2, 1. -2, 1, and 2. All right, those are the only values in the range. All right, so -1 has been associated with 1. Right here at this point. 0 has been associated with -2. Over here, 2 has been associated or assigned to 1. And 3 has been associated with 2. So even though 2 of these x's were associated with 1, that's not a problem. This does in fact qualify as a function because what happened? Oh my God, what happened? All right, my diagram got messed up. Hold on a second. Oh, was something weird happening to the computer while I was away? Huh. It works now, doesn't it? Oh, you know what? You know what that might be? I'm having an issue with the lamp in this room. One of these bulbs has got a problem. It's just it might be the ceiling fan that I have with the lights. It is having an issue here, and I have informed my landlord of this, and they're supposedly going to come and fix it. There's something about this socket here where the bulb is sort of coming and going, and that might be what you were seeing. Yeah, it's very weird looking. It looks like I was filming a horror movie here, doesn't it? But if that's what you were seeing, that's all it is. My light bulb is misbehaving, and you know, I don't know what to do about it. It's just sort of randomly flickering on and off. It just means something is loose up there, and I don't want to touch it. I'm not an electrician. So if that was the problem, that's what it was. There's nothing wrong with your computer. Okay. All right. Yeah, no, sorry about that. I didn't realize that you could see it happening. Anyway, let's get back to this. So the point of it is that, let me fix my diagram. 2 is associated with 1 and 3 is associated with 2. All right, so here's what we need to know. Is it true that each of these x's has one line coming out of it? I guess you could describe it that way. In other words, each x in the domain, so each x in the domain is associated with exactly one y in the range. Okay, that's what we're aiming for. The fact that two of these x's are associated with 1 is not a problem. That's okay. What is not okay is if each x has more than one y. But here you can see each x is associated with exactly one element of y. So this means that, or therefore this is a function. Okay, so that's what we need to know. So I think that drawing the picture could be very helpful here because you can actually see for yourself just by looking at it that each x is associated with exactly one y. Without the picture, I mean, you can still probably get it, but I think having the picture makes a big difference. It really does. So let's try this one. Yep, you can see it's acting up there, isn't it? Yeah, it's having a rough day. I don't know what's going on up there. So don't be disturbed by it. I can't do anything about it right now. So anyway, the x's are, let's see, what do we have here? We got, let's try this. Oh, okay, here we go. So we have -1. We have a 0. It is having a rough day. I think it's getting worse. But see, the problem here is that because of the damn COVID, the repairs are way behind schedule. It could be a long time before they get over here. So I may have to just leave the damn thing off. In fact, you know what? I'll tell you what. There you go. It's not going to happen now because I turned it off. Yeah. All right. So there you go. Is it very dark and gloomy now? Well, I guess it's better than flickering. Oh, all right. Well, that's fine then. Yeah, you're right. The sun is coming in. It should be okay. It's kind of a dreary looking day out there, but at least the sun is out. All right, anyway, so we have for our x's, we have -1, we have a 0, and we have a 1. Now you can see we're going to have a problem here. If you look at the y's, we've got, oh man, look at that. So the first one is 1, 1, 0, 1. Okay, so far so good. -1, 1. Okay, again, not a problem. But here there is a problem. So there you go. The number 1 in the domain has been associated with both. Let's see, the element 1 in the domain has been associated with both 1 and 2 in the range. Therefore, this is not a function. And if you just want to think about it from terms of the graph, anytime you see one of these points having more than one line coming out of it, already you know this is not a function. So that means no for this one. Now this one, let's see what's going on with this one. So we've got, let's try this one. For the x's, we have 0, 1, negative, okay. -2, we have a 1, sorry, we have a 0. I like to put them in order. They don't have to be in order, but I like it that way. Over here for the y's, we've got a -2. We've got a 0, a 1. Oh, how do you like that? Okay, so we have a 0, 0, 1, -2, -2, 1, and 3, 3. Oh, this one is fine. All right, so each x, or each element of the domain is uniquely associated with a single value or single element in the range. In other words, a y. Okay, so you can refer to them as elements of the domain of the range, or you can call them x's and y's. Either way, this one is fine. Therefore, this is a function. All right, so that's how those work. Now, later on, we had some, when you're dealing with more advanced cases, we saw the horizontal and the vertical line test. We'll get back to that again later on here in these questions. Now, here we're looking for domains and ranges. Now, this sometimes can be a bit of an art trying to figure these out. For example, and by the way, always keep in mind, you're trying to avoid any situations where you have either division by 0 or possibly a negative square root. So it also helps if you can visualize what the function looks like. So for these, to be on the safe side, you might want to take a look at Symbolab. It should help you visualize what is going on here. So let's see, here we are. This is a very simple one. We're just looking at y equals 1 over x Yes, so you can plainly see two things. Number one, the function will never quite touch the horizontal axis. In fact, it even shows you here, this is the horizontal asymptote. It will also never quite touch y, the vertical asymptote, vertical axis. So it has two asymptotes, as they're called. These are lines or numbers that the function converges to, but never quite actually reaches. So therefore, we cannot have a value of x equal to 0 or a value of y equal to 0. Okay, so therefore, we would claim, or we would conclude from all this, that the domain is basically all values except 0. In fact, hold on a second. So this is how we traditionally write this. Now, this is the technique favored by the book. In principle, you could also express this as something like this. I guess you could just write it as x is not equal to 0. I believe if you look in Symbolab, they have it written both ways. Yeah, here it is. Interval, I see what they've done. So this is what we're used to seeing in our book. But here what they've done is they've written it as, and this is more informal, which is why you don't see it as often. You could also in principle write x is positive or negative, but not 0. All right, so that's our domain. Now the range, remember, means that we cannot have y equals 0. So that means the range will be identical to the domain. And again, if you feel like writing it like this, actually, in this case, sorry, it would be y, not x, y. Although in Symbolab, they're writing it as f of x instead of y, but that's okay. So either way, the whole point of all this is that the domain is everything except 0. And so is the range. And so however you want to express that, in fact, if you, God, you could even just probably write the words, the domain is all x's except for 0, and the range is all the y's except for 0. Technically, I mean, it's not formal, but it does the job. But anyway, so now what about this one? Now you can see that there's going to be a potential problem. Okay, so by looking at it clearly, in order to avoid having a negative square root, or in other words, an imaginary number, x must be at least 2. Okay, now because this is a square root, y can only be 0 or positive. So these are just observations that we're making to help us figure out what the domain and the range are. So if we go to Symbolab, and just to take a look at it, y equals radical x minus 2. And you can visually see that the x's start at 2. There's no x that comes before 2. And as far as y is concerned, there aren't any negative y's, although it can be 0. So we'll tie this together and say, all right, well, if that's the case, then the domain must be, sorry. This time we will need the square bracket because we can have a 2. For the range, we can have 0 and everything above that. All right, does that make sense? Okay, good. Now let's look at this one. Now you can see here, where are we likely to run into trouble? Well, it's pretty clear that x cannot be 3, since this would lead to division by 0. Okay, is there anything else that's disallowed? Good question. I would say, now, because though there is a hole basically in the domain, most likely there's an asymptote involved in this function. So why don't we go to Symbolab and just graph it 2 over x minus 3. Just to see what it looks like, so we can try to figure out what is going on with the range. Okay, the domain is usually easier to visualize than the range, but let's find out what's going on here. Oh, so just as we suspected, yeah, there it is. So this is x equals 3. So in other words, y itself cannot, as you can plainly see, y cannot equal 0. Okay, so anything else goes, because x equals 3 is a vertical asymptote. the function converges to but never quite reaches it. But also the horizontal axis is another asymptote. So there is no possibility that x equals 3, and there's no possibility that y equals 0. So y cannot equal 0 since there is no ratio of positive or negative numbers that gives a value of 0. All right, so we're basically saying then that we're leaving out x cannot be 3 and y cannot be 0. So therefore the domain can be written as negative infinity up to but not including 3. So we use the round bracket. And then again, not including 3 up to positive infinity. The range is similar, but it's 0 instead of 3 that we disallow. Okay, oops. Now, why don't we do this? If you go into the symbol lab, it tells you anyway. I mean, it's right there. So negative infinity up to 3, 3 up to infinity, and down here it's negative infinity up to 0, and 0 up to infinity. Now, what it does is tell you the answer. It does not tell you why for the most part. Oh. See, now it offered to show me the steps here, but this one you have to pay for it, I guess. So if you whip out the credit card and pay for this, I guess you can get all these extra details if you need them. Yeah, that's not very helpful, is it? But anyway, so we get the idea. And now for number 8, now this is an interesting case because we are allowed, we can take cube root of a negative number. Okay, therefore, there are no restrictions on x. And since the function, well, the cube root can produce positive or negative numbers or 0, there are no restrictions on the value of y. Okay, so therefore, the domain and the range are both all real numbers. Okay. All right, so we write it out as the domain is this, and the range is the same thing. Okay. Now here we have the average rate of change. So for this, we need to go back to the slides and remind ourselves where we covered this material. And so let's take a look. This is clearly chapter 1 material. Let's find out where we actually discussed this. All right, let's see. I'm going to try the search engine and see if it'll actually give me average change or something like average rate of change. Let me try that. Ooh, that was lucky. Okay, here it is. So we're going to go to slide 109 in 1A. So this one can be found in chapter 1A slide 109. And what we really want is the formula. It's this. That's all you need right there. So let's copy that in here so we can refer to it. Okay, now, how do we read this? Well, the way we have to think about this is that x1 is the -2. x2 is the 8 in that interval. Okay, so that's what this is telling me. It's this function over this interval. We have to figure out for ourselves the values of f of x1 and f of x2 before we apply that formula. Yes, we have to do everything ourselves around here. All right, so in this case, we'll have f of -2 equals 6 -2 squared, which is, of course, 6 times 4, which is 24. Okay. And then f of x2 would be f of 8, which is 6 times 8 squared, which is 6 times 64, which is 384. Now we can plug everything in. All right, this is our formula. So we got everything we need. We just plug them in. (384 minus 24 is divided by 8 minus -2 equals 360 over 10, which is 36. All right, so the average rate of change over that interval is 36. Now that discussion will come up again in one of the last chapters in the book, the average rate of change. We're going to see a much more formal way of doing that. But here you can see that literally all you're doing is calculating the change in the y's relative to the changes in the x's. Okay, now we could look at this graph in Symbolab, but there's no real need for it. It's just, it would be this. A standard parabola. And so basically what you're being asked to do is to say, well, between this interval right here, between -2 and +8, what's the average rate of change between those 2 points? That's essentially what you're doing. All right, now number 10 rather, is exactly the same, except that the interval and the function are different. So here we'll define x1 to be the -8, and the x2 to be the -5. That's the easy part. What about the f's? F of x1, for example. Ooh, that's a tricky one. That will be, well, first let's recognize that this is f of -8. Over 4 minus -8. All All right, so that equals 64 over 4 plus 8, 64 over 12. Okay, wow. So then, although if you want to, you could reduce that to 32 over 6, and that can further be reduced to 16 thirds. Okay, f of x2 4 minus 5, 25 over 4 plus 5 equals 25 over 9. All right, well, I'll tell you what, it's probably going to be easier if we convert this one into ninths. Let's make that 48 over 9. How about that? All right, so now with our function, here we go. Let's try this one. We've got, this is a mess, 25 ninths minus 48 ninths in the denominator. We have minus 5 minus a minus 8. All right, so in the denominator we have minus 5 plus 8 is 3. In the numerator, though, we have the difference between those two is minus 23 ninths. Okay, now this is a mess. That's right. We know what to do with this one. So I'll show you what you can do in a case like this. You could think of this as 23 ninths divided by 3 over 1. And then you can multiply this times the inverse, which is 1/3. So you'll end up with minus 27 over, minus 23. Minus 23 over 27 is the final answer. All right. All right, so now for this one, x1 is minus 3, and x2 is 3. All right, so f of x1 is f of negative 3, which equals 7 plus 4 times minus 3 squared equals 7 plus 4 times 9. 7 plus 36 is 43. F of x2 equals f of positive 3, which is 7 plus 4 times 3 squared. 7 plus 4 times 9. Well, what do you know? It's 7 plus 36, 43. So it's the same. So basically what happened was you basically have value at two different points, they're both the same. This is the point 3 comma 43. This is the point -3 43. And so you can see, because we end up at the same point that we started at, the average change is 0. We basically just went right back to where we started from as far as y is concerned. So when you fill in this formula, you'll see that you're just going to get a 0. A very strange case, but that's exactly what just happened. So in the numerator, we have 43 minus 43. In the denominator, we have 3 minus a minus 3. Yeah. Okay, so, but the denominator is actually kind of irrelevant here because we have 0 in the numerator, we have 6 in the denominator, and that just leaves us with a 0 rather. Okay. Very good. So that was unusual. And how about this one? We've got x1 is 0 and x2 there you go. So what about f of x1? So that's f of 0. So that's going to be, I'll need the equation editor for this one, or else I'll do it by hand. Okay, f of x0, x1 rather, f of 0. So in this case, it would be 5 radical 0 minus 2 times 0. Oh, that was easy. That's just 0. F of x2 is f of 5. 5 radical 5 minus 2 times 5 is 5 radical 5 minus 10. So for this formula, we have 5 radical 5 minus 10 minus 0 all over 5 minus 0. Now, it just so happens that each of these is evenly divisible by 5, so we end up with radical 5 minus 2. All right, well, that worked out pretty well. All right, now the next group, look what we have here. We have composite functions coming up. All right, well, we know what to do with them. So, before we forget, let me just go back and find in the slides where we introduced this topic. Oh, lucky, first hit, first attempt, I found it. This is chapter 1A, slide 128. Okay, now we can continue. So these are very straightforward. The ones you're seeing here, these are just simple algebraic operations. The ones directly below are actually the composite functions. Those are the tricky ones. But let's just do these. So in this case, we have, now look how easy this is. You just take the two functions, x squared minus 3x plus 5 plus x. We drop the parentheses, we have x squared minus 3x plus 5 plus x, and then we just consolidate them. So we have x squared minus 2x plus 5. Now, for the second case, we're doing the same thing, except that it is now subtraction. So it's x squared minus 3x minus 5 minus x. And be sure to distribute the negatives across the parentheses. Oh, you mean this one? No, but we've got negative 3x and positive 1x, so that's negative 2x. Okay, so in other words, these two are giving me the negative 2x. Okay, so yeah, we just have to be a little careful with these guys. So anyway, so here you can see I've got x squared. Now there's a negative 3x and a negative x, so that's negative 4x, and then the constant is negative 5. You're welcome. No problem. Okay, so those two are pretty simple. If only they were all like that. Now here we've got to multiply them. So you know what? It turns out, well, just our luck, we can easily do this with FOIL. All right, so we've got x squared minus 3x, 5 plus x. Let's do FOIL. Here's our first 5x squared. Outer is x cubed. Inner is minus 15x. Last is minus 3x squared. So here we have to watch it because we have at least some terms that can be combined. All right, these two can be combined. So we'll have 2x squared. Oh, let's put the x cubed over here. This should come first because it has a higher exponent. So this is actually the final answer. X cubed plus 2x squared minus 15. Oh, I'm sorry, I left out the x. Minus 15x. And we're done. Well, that was nice. All right, now the last one is a ratio. In this case, we've got f of x is x squared minus 3x. And g of x is 5 plus x. There isn't really any way of simplifying this. Now, it doesn't specifically ask you to do any division, and it wouldn't do any good either because you'd end up with a really strange quotient. So in a case like this, unless it obviously simplifies, I would just leave it like this. All right, because this is correct. There's nothing wrong with this. It may not, it's possible to find something simpler, but this is fine as far as it goes. I would just leave it like this. And then down here, this, of course, came from the same slides. Let me just copy that so we don't forget. Now, these are the challenging ones. What exactly are we doing here? So because f of x in this first case is 2x squared minus 5, f of g of x means you replace each x with g of x. Okay, replace each x with g of x. Now you make the substitution. In other words, this is a good idea just so you can visualize what you're doing. But now you have to actually substitute the expression here, minus 2x plus 7 squared minus 5. And then ideally, in a case like this, you should probably simplify it a little. It's not absolutely necessary. In fact, I'll tell you what, why don't we just leave it like this? If you want to stretch it out and expand on it, it's fine, but I think this is good enough. All right, so the key to the whole thing is that wherever there was an x, that was replaced by g of x. Now down here, we're essentially doing this in reverse. We have g of x is minus 2x plus 7. To find g of f of x, replace each x with f of x. Okay, so that's how this one is done. So what I'm going to have here is that g of f of x is minus 2 f of x plus 7. And then you actually substitute the 2x squared minus 5 plus 7. And again, it's kind of a messy function. So is it absolutely necessary to consolidate? Probably not. You can feel free to leave it like this. Okay, unless you want to expand it. You can, but it's not necessary. All right, now the next one is f of g of 0. See, now this is a nice one because we already know from earlier and if we had, you could start this from scratch, that f of g of x equals 2 times negative 2x plus 7 squared minus 5. So therefore, f of replace all x's with zeros. That's what it's telling us to do. So we'll have two, and inside the parentheses, this is 0 plus 7. And that gives us 93. All right, now for this next one, we have g of f of 3. We've already demonstrated or calculated g of f of x. So we might as well take advantage of that knowledge. So g of f of x, we showed up here, was minus 2 2x squared minus 5 plus 7. And so therefore, what we're going to do now is replace each x with 3. And of course, solve it. So therefore, we'll have minus 2 times 3 squared minus 5 plus 7 This is 2 times 9, 18 minus 5. Equals minus 26 plus 7, negative 19. All right. All right, now these last two, these symbols, this one actually is shorthand for f of x. Okay, just remember that. Now the original function here was, let's go grab it. F of x equals 2x squared minus 5. So therefore, when we calculate f of x, replace each x with f of x. Okay, so you're going to have 2 f of x squared minus 5. So therefore, you'll have 2x squared minus 5 squared minus 5. And again, you can expand this if you want to, but you can just leave it too. So this FOF thing equals all of this. It's just notation. It's called a composite function, f with itself. It's just f of x. Sounds weird, but yes, it's a function of itself. It would be kind of like saying, take the square root of the square root, that kind of thing. All right, now g of g, I mean, you can see this functional notation simply means g of x. And so what this means is replace each x with g of x. So let's go back and revisit g of x. So therefore, g of x equals g of, sorry, not g of, negative 2 g of x plus 7 Now, I'll tell you what, in this case, this is so simple, we may as well go ahead and expand on it. 4x minus 14 plus 7. Okay. That one is fine. In a simple case like that, you know, what the heck. Let's do it. All right, now in the next block, okay, we'll have to go look up where this was discussed in the first place. Okay, let me go find that. Let's try 1A. about 1b? All right, this looks promising. Yeah, this is it. All right, this is fine. This is chapter 1b, slide 74. So basically, this is where we are introduced to the idea that this is how you demonstrate whether or not two functions are actually inverses or not. Okay, in fact, I'm actually going to copy this because it's so helpful. So this is what we're trying to demonstrate in each of these cases. So for the first one, now here instead of f and f inverse, we have f and g. So we start out by trying to demonstrate that f of g of x equals x. So f of g of x means take each of these, wherever there is an x, replace it with a g of x. So this x becomes g of x. All right, and then you make the actual substitution. All right, now in the denominator, we have the 4's drop out. Okay, so this part is done. That was easy. What about g of f of x? So we take our g of x and replace the x with f of x. All right, and remember f of x is 1 over x minus 4. Now this one is kind of awkward. How do we convert this one? Well, let's see. What we need is a common denominator. Which we will typically choose to be the ratio of the messier function. So here's what we've got. 1 plus 4x minus 4 over x minus 4. Oh, now something, wait a minute. Now something's not right here. The first part is fine. Let me look at this again. 1 over f of x plus 4. Oh, I know where I screwed it up. No, sorry, my fault. No. I could see something wasn't right. It's because f of x is itself 1 over x minus 4. So therefore, this is not right. F of x is 1 over. So when I did this, I did it incorrectly. This should have been 1 over x minus 4. Now we're getting somewhere, okay? Because the f of x itself was 1 over x minus 4. It's an easy thing to screw it up. Now, this ratio, 1 over, let's say x, is just equal to x. So therefore, this is x minus 4 plus 4 equals x. So we've proven both halves of the requirement to show right here whether or not these two functions are inverses. So we're done. Now, we already knew that they were inverses. That wasn't our job. Our job is to prove it. All right. Now, they're all exactly the same. It's just a question of not messing up the algebra, really, when you come right down to it. All right, so now for here, let's start by showing that f of g of x equals x, all right? So what we have to do here is take our original f of x and replace every x with g of x. All right, now we make the actual substitution. And then these threes clearly cancel out. And so that one's done. Whoops. Oh, you mean at like this? Okay, that would be f inverse of f of x. Yes, if you run into that. Okay. All right. Anyway, so let's carry on. Then we have to do the reverse g of x, g of f of x rather. So remember what we're doing is we're taking each x and now we replace it with f of x. Okay, so then the f of x is 3x minus 2. So then here we clearly have the 2's cancel out. We have 3x over 3 equals x. All right, so that does, our job is done. We've proven that both of these equal x, so we're done there. Give ourselves a big check mark, which means we did it. All right, now these two. All right, so we'll begin with f of g of x. So remember, it's just a question of replacing each x with g of x. These 4's cancel out. So you got to be very careful here with the negatives. Oh man, so that one worked very well. It would have been so easy to mess that one up. All right. So now we have to go the opposite direction. So we start with g of x. G of x is 4 minus x, so this becomes 4 minus f of x over 4. Okay, now we make the substitution. We have to distribute the negative across the parentheses. These two drop out, so we're left with 4x over 4. And there you go. We did it again. All right. So now how about these two? There's just two more, one more. You can see after a while, they start to become pretty familiar. So once again, f of g of x. All right, so replace that g of x. And again, like I almost messed it up last time, this is 1 over x minus 2, which is the same thing, though, as x minus 2. All right. And then down here, 1 over x minus 2, 1 over f of x minus 2, 1 over 2 plus 1 over x minus 2. So you can see what's happening here. The 2's will drop out. But 1 over x is the same thing as x. And so we're done. Okay. Now here we're going to be evaluating some complex numbers. So that one showed up at, we did it very recently. I think it was 3A. Let's just confirm that. Ooh, yes, here it is. So we'll just note that this comes from the beginning of chapter 3A. How about that? That should be good enough. You should have no trouble finding it. Now, all you're doing is you're plugging in 2i minus 7 wherever you see an x. Okay, so in other words, f of 2i minus 7 equals 2. It's 3 minus 4. And then you just evaluate it. Now here we will evaluate it. So we can use FOIL. Now it'll be interesting to apply FOIL to an imaginary number. Let's see what happens. Whoops. So first is 4i squared. So we'll leave it the way it is now. We'll simplify it later on if we need to. Here's O. The inner is also minus 14i. And then last is 49. So we've got 4i squared minus 28i plus 49. But remember, I squared is negative 1. So we can replace this with all of this. We've got minus 4 minus 28i plus 49. And so when we're done, we've got minus 28i plus 45. That is what we have inside the square here. So in other words, I can now replace this with 2 minus 28i plus 45 plus 3 times 2i minus 7 minus 4. Now I'm going to, of course, multiply across these parentheses. Minus 56i plus 90 plus 6i minus 21 minus 4. And so we've got between the two, let's see, minus 56 and plus 6i. Let's combine these two. We'll have minus 50i. And then if you combine 90 minus 21 minus 25, you'll get 65. Okay, so let me just double check that. Yeah, minus 50i plus 65, or in the more traditional format, not that it matters, you can write it as 65 minus 50i. Usually with complex numbers, we write the I second, not that it really matters. I would never take points off for doing it like this, but this is the way mathematicians want to see it. Ooh, that was tricky. But again, remember, this took advantage of our knowledge of the fact that I squared is negative 1. So otherwise, we would have had quite a messy expression. Instead, it's simplified very nicely. That's always good. When things are simpler, they're always better. All right, what about the next one? Well, again, this will get us involved with some identities. F of I, look at this. So, well, look at now, this is the answer, but remember, I to the fifth equals I to the first, which is just I. I cubed is the same thing as I squared times I, which is negative I. So this could be rewritten as I minus 2 times negative I, which is I plus 2I. So you can reduce it very nicely to 3I. Boy, that's interesting. Like this expression, which looks pretty scary, reduces very simply to 3I. And that's, of course, because of our knowledge of the exponents. All right, let's try this one. So I literally just replace all the x's with 6I. Now here I have 36I squared minus 12I plus 1. Down here, I'll have 2 minus 30I. Now, the only place we can simplify this one is that I squared on the numerator, because of course that's equal to negative 1. Okay, so then we have minus 36 minus 12I plus 1. Okay, and so then when you consolidate the constants, you'll have minus 35 minus 12I all divided by 2 minus 30I. And at this point, you can stop. There isn't any realistic way of simplifying this any further. And that's it, you're done. Now, this next one is the last one, which is good because this one is actually quite a mess, but it's good practice. When that's done, we can move on to the, oh, okay. Well, we've got more eyes in our future here anyway. So, all right, so let's see what's going on here. So this one is a bit more complicated, but we can do it. Okay, ooh, look at this. You know what, I'll tell you what, I'll make sure this one doesn't sneak into the exam. This one, you've got a cube here, for God's sake. Ooh, this one's going to be brutal. All right, well, I'll tell you what, here's what we should do. Let's evaluate the square and the cube terms separately. The reason why it may not be quite as bad as all that is because once we know 4i plus 9 squared, we can then just simply multiply it again by 4i plus 9 to come up with this expression. So 4i plus 9, we can do it with FOIL, and it will actually be simplified by the powers of I. So maybe it's not quite as bad as it looks, but it's going to be challenging, shall we say. All right, So let's see what we get. F O 36i, I, same thing, 36i, last 81. So you have 16i squared plus 72i plus 81. And of course, this one is simply 16 times -1. And oops, we have -16, 72i plus 81. So we can simplify that as 65 plus 72i. Now, in order to get I cubed, 4i plus 9 cubed. So this is the final result of 4i plus 9 squared equals this, which means that if I want to cube this, I can take this result and multiply it by 4i plus 9. And now, once again, it's a simple FOIL problem. So this might work out pretty well. F, okay, that's 260i. O is 585. I is 288 I squared. And then last would be 648 I. All right. So, man, those are some challenging ones. No, 72 times. Yeah. Okay. So now we'll bring them together. All right. So we've got 2 i's. We'll combine those, and that gives us 8908 I. Oh, here we go. This is equal to of course, 288 times -1, because that's I squared. So we have very simply 908i. And then I'm just subtracting this from this. So I've got 297. So what have I accomplished here? Well, if you go back to the original equation, I can make 2 major substitutions now. Okay, so once again, the 4i plus 9 squared can be replaced with 65 plus 72i. And this cube down here can be replaced with 908i plus 297. Now, that's still a messy expression, but it's not nearly as bad as it was earlier. Okay. Man. This could be like a triple bonus point question. All right, 908 I plus 297 plus 3. All right, well, now we just simplified a little. 1 plus, so here we have 8i plus 18 minus 195 plus 216i. All All right, now here we have 908i, and these two clearly add up to 300. All right, so we're getting close. So we've got these constants equal minus 176 plus 224i. And down here, let's write this as 300 plus 908i to put it in the more traditional format. Okay. Man, that was a doozy, huh? All right. Well, now luckily the next couple are going to be more straightforward. Like, for example, these are just foils. All right. Well, they're tricky foils because we have higher powers of I, though. F is here. O minus 3i squared. I, 32i squared, and last, minus 8i cubed. And recall, I squared is -1, I cubed is simply -i. I'm sorry, wait a minute. I cubed. That's right. No, this is it. Okay, good. All right, so that being the case, you have 12i plus 29 times -1 minus 8 -i. So you've actually got 20 minus 29i as your final answer. Oh, I wrote it wrong. Sorry, my fault. I just realized I copied it wrong. It's 20i minus 29. That's better. All right. Well, after all that work, I almost blew it, didn't I? Yeah. All right. Well, let's try this one. Now, this one's looking really tough. There's a lot of higher order powers of I here. This one should be a bit of a challenge. So F is here. 12i cubed. O minus 18i to the fourth. I is minus 6i to the fourth. And last would be 9i to the fifth. Oh, man, this one is tough. 12i cubed minus 24i to the fourth plus 9i to the fifth. All right, so remember, I squared is -1, I cubed is I to the fourth is +1, I to the fifth is just I. So therefore, we have 12 -i minus 24 times 1 plus 9 times I. So I've got minus 3i minus 24. Man. Yeah, we got a ways to go here, don't we? Ooh, there's a lot of work here. I was afraid of this. I was pretty confident we were not going to finish today. You know what? I'll tell you what. Why don't we stop right here? Because there's so much more to go. But like I said, I will post these today as partial solutions, and I'll put up, the exams. You can start to look at it. But because of the fact that we're not done reviewing, what I'll do is I'll give you an extra week to finish it. So in other words, it won't be due for 2 more weeks. And you're under no obligation to start it right now. You can wait a week, you can do whatever you want, but this way, at least if anyone feels ambitious enough to start right away, that's fine, but it's not necessary. Okay, so I guess we're going to stop right here because I know you're probably getting worn out anyway. This is a lot of material to do all in one shot. So, and plus, if we're really close to the end, I'd just finish it, but we're not. Yeah, 2 weeks. I was going to give you 1 week, but under the circumstances, you can have 2 weeks. All right. So I'll post it up there today with these partial solutions. And that way you can feel free to start the test now or wait till we've done the second half. That's up to you. It's completely your decision. But I know that there's always some people who just want to get it out of the way, and that's fine too. So we'll finish this up next time, and then we'll start new material, of course, which is chapter 4. But this really has to be done before you can do the test. Or if you don't feel that way, you can certainly try it in advance, or you can do some of it, it's up to you. So like I said, so you can have 2 weeks, which, God, given how long this took, it might take 2 weeks. No, it's not nearly as long as what we did here. I mean, the test that you're getting was meant to be done in the classroom. So it can't be this long. Otherwise, we would have run out of time. So it's basically a smaller version of what we just did today. Okay, but it's very similar. There's no surprises hiding in there. Everything in there should be very straightforward, very much like what we've done. I did not go out of my way to make it more complicated. If anything, I went out of my way to make it a little simpler. So everybody should be in pretty good shape then. Well, but make sure you go through the solutions and make sure you understand what we've done. All right. And of course, as usual, you can send me emails if you want to. And if there's no last minute questions, I guess we'll just stop right here, and I'll see you all next Wednesday. Okay.
Thank you for your time, Professor.
All right.
Very much
See you
appreciated.
next week.
Thank you, Professor.
Okay. See you later.